Alright, on this problem, you have a mass spectrometer here. A mass spectrometer is just a device that uses electromagnetic fields to determine the mass of an object. And you're told that you have a strontium atom, you have a strontium ion, you have a magnetic field, and you have an exit distance of x, where x is given to you. The first thing you're asked is to figure out what direction must the magnetic field point to produce the trajectory of the ion, and so on. So the magnetic field is going to be in this box here. And the force on this charged particle is circular, or creates a circular motion, so the force is pointing toward the center of the circle. So you use your second right-hand rule. Your thumb is your velocity, so point your velocity, your thumb in the direction of any of these, let's call these red arrows here. And any of these red arrows, because that's the direction of the velocity. So if your thumb is pointing this direction and you point your palm in the direction of the force, which are these smaller black arrows, your fingers will tell you what the field is, and they should point into the page. So the answer for number 1 will be into the page. And I draw X's on there to represent they're into the page. Now, you're told the ions travel at constant speed around the semicircular path. Explain why the speed remains constant. The reason this is that that if your velocity, let's say at the top of the arc, your velocity is pointing this way. In your right-hand rule, if you point your thumb in the direction of velocity, your fingers are going into the page. The right-hand rule tells you that the direction of your force will be perpendicular. That's your magnetic force. And since these two objects are perpendicular, the magnetic force will change the direction, but it won't directly change the velocity of the ion. Now, it says to calculate the speed of the ions with charge plus 2e the exit at distance x, where distance x is given to you as 1.75 meters. So, the only force that they experience is a magnetic force while they're in the selector, so we know that magnetic force is equal to QVB, that's magnetic force on a charged particle. And since the shape of these becomes circular, we can say that this magnetic force is a centripetal force, so that force equals mv squared over r. And you're asked to figure out what is the velocity. First thing I'm going to do is I'm going to cancel out one of these velocities here. You don't have to if you don't want to, but it does make it a bit easier to solve. Then we're going to multiply each side by r, so we get that QBR divided by m equals our velocity. Now all we're doing, we're just isolating this velocity term here, multiplying by r divided by m. Now, we know a lot of these charges here. We're given q. Now we're told that q is plus 2e, where e is the charge of an electron. So if we're twice the charge of an electron, but we're positive, that means we're basically twice the charge of a proton. Now if you know that the electron is 1.6 times 10 to the negative 19th coulombs, then 2e is going to be 3.2 times 10 to the negative 19th coulombs, or 2 times 1.6. So we can say 3.2 times 10 to the negative 19th coulombs. That's going to be our charge. Our magnetic field is given to us as 0.09 Tesla. And our radius, we have to find. So we're told that x is going to be this distance from where they enter to where they strike the wall at. So the radius will be half of x. So if we say 1.75 divided by 2, that'll give us our radius, which is let's see here, 0.875 looks like. Plug this in down here, 0.875 meters. That's going to be a radius. And then we're going to divide by our mass value. So we have our formula right there. Our mass is given to us as 1.45 times 10 to the negative 25th kilograms. And if we multiply the top divided by the bottom, we get a velocity of 1.74 times 10 to the 5th meters per second. And that's reasonable because you know that most times these charged particles are around are around the tens of thousands and hundreds of thousands velocity. Alright, the next thing it says is to calculate the accelerating voltage sigma, or excuse me, epsilon, needed for ions with a charge of plus 2e to attain the speed you calculated in part C. So we're talking about the circuit part of it here. Now, how this works is that you have a battery, and the battery has a positive charge on one end, negative charge on the other end, takes these positive particles, accelerates them through this difference here. So initially we're going to assume it's not moving, so all the particle has is potential energy, and then as it flies through the voltage, all that potential goes away and it turns to kinetic energy. Now, potential energy of a charged particle is QV, that's from your formula sheet, and kinetic energy is always 1/2 mv squared, and we're looking for what is this big voltage here. Now we're told that the charge is plus 2e, so that's going to be 3.2 times 10 to the negative 19th coulombs, like we did a minute ago. We're looking for a voltage. Our mass is given to us as 1.45 times 10 to the negative 25th kilograms. Negative, and that's kilograms. And our velocity is 1.75 times 10 to the 5th meters per second. And we get to square that value. I'm going to run in a space here. So, multiply all your kinetic energy together, divided by the charge, and you should get a voltage of 6859.4 volts. That's just straight from the conservation of energy.